Hello everyone. In the lecture today, we will continue the topic in distance measurement. In our previous lecture, we already go through the basic concept of the horizontal distance measurement. Today, we will try to analyze the errors in the horizontal distance measurement, especially the taping method. In general, there are three types of the errors in the taping method. The first one is called instrumental error. This error happens when the tape does not have standard length. In that sense, the markings from the tape does not reflect the actual values it's claimed, so that tape cannot measure any distance accurately. The second one is called a natural error, including the errors from the temperature, tension, and sag. We know that usually with the temperature, we will observe expansion or contraction to the tape, which will generate some errors for the taping measurement. Applying tension to the tape will usually reduce the readings from the tape, while for the sag, which is usually caused by the weight of the tape itself, it will actually increase the readings from the tape. Finally, the last error is called a personal error, which is caused by the operational errors from the surveyors. In general, if the tape is not horizontally aligned for the 2 points, then it will cause some error. The distance measured from the tape is not the horizontal distance between the 2 points. Also, it could happen if the tape is not accurately aligned to the starting point or the end point. In addition, if the tape is not straight, then it cannot measure the line between 2 points. And those are all caused by the operational errors from the surveyor. We know that there are some errors in the distance measurement, but what we are more interested in is how to correct them. In general, for the instrumental and natural errors, they can be corrected mathematically, and usually the correction is a function of the set of nature properties or the instrument features. While for the personal errors, they can only be corrected by repeating the measurements. We can also borrow the advantages of some assistant tools to monitor the experiments so that we can identify the potential personal errors and avoid them in the future. Now let's see some errors that can be mathematically modeled and corrected. The first one we are interested in is the variation in temperature. In general, we know that the tape will expand as the temperature raises and contracts as the temperature falls. In that sense, if you have the actual distance of 1 meter, then with the tape, if the temperature increases, the reading from the tape will actually be smaller. It could be like 98 centimeters if we increase the temperature. But if the temperature drops, the one you observed may be higher. It could be around 101 centimeter. So we can see that the reading from the tape under different temperatures will be different, and that requires us to introduce some corrections from the temperature. In general, we assume that the errors from the temperature is a linear function to the temperature. So we said that correction capture Ct is alpha times L times T minus T0. Here, alpha is the coefficient of the thermal expansion, L is the measured length, capital T is the applied temperature during the experiment, and T0 is the standard temperature. Usually for most of the tape, the standard temperature is set as 20 Celsius or 68 Fahrenheit. The second error we're going to consider is variation in tension. In general, there is a standard tension applied for the tape to ensure that all the readings from the tape is correct. However, if the tension or the pull is larger or less than that value, then the tape will be elongated or shortened accordingly. Let's take the example about the 1 meter measurement again. So we have the 1 meter object. If we apply a very high tension and it's larger than the standard tension, then the reading from this tape might be smaller. It could be 97 centimeters. But if we don't have the very high tension, say that P is smaller than P0, then the reading from the tape may be like 102 centimeters. In order to handle the error caused by the tension, we need to apply a correction. So the correction from the tension is capital CP as P minus P0 times L over A times E. Here, A is the cross-section area of the tape. Capital E is the elastic modulus of steel, and L is the Mayer length, P is the applied tension, P0 is the standard tension. Now let's see one example about the variation in tension. Here we assume that a light 100 feet tape is standard with the full support under a tension of 10 pounds with the elastic modulus of 30 million pounds per inch square, and the cross-sectional area of the tape is set as 0.003 inch square. And it wants us to determine the elongation for an increase in tension from 10 to 30 pounds. Also, we assume that tape is used with full support. To solve this equation, we will first list all the conditions we have and the problem we want to get. First, we are given the length of the tape as 100 feet and the standard tension P0 is 10 pounds. Also, we know the elastic modulus is 30 million pounds per inch square, and the cross-sectional area is 0.003 inch square. We want to find out the elongation, which is the correction from the tension. So that is CP. So in the solution, we will try to call the equation in the previous page. So we will have CP equal to L times P minus P0 over A times E. That will give us the result as 100 feet times 30 pounds minus 10 over 0.003 times 30 million. So the result is 0.022 feet. So the elongation from the increased tension is 0.022 feet. The third error that we will consider is sag. The sag is actually occurs between the points or the support. It's generally caused by the weight of the tape itself. So here, if you have two support for the tape, well, you want to measure the distance from A to B, and the tape will be placed from A to B. Due to the weight of the tape itself, the tape is not actually a straight line from A to B, and actually it's in the form of the catenary. So the actual distance caused by this curve will be the error from the sag. In general, we will apply the equation here to correct the error from the sag. So the correction is capital CS equal to little w squared plus L cubed over 24 times P squared. Or it could be written as capital W squared times L over 24 times P squared. So here, little w is the weight of the tape, is actually defined as the unit weight of the tape. So the unit is pound per feet or kilogram per meter. Capital W is the total weight of the tape between the support. So it's not the whole tape length. And capital L is the measured length, capital P is the applied tension. So here we see that the correction for the sag is also related to the applied tension. This figure actually shows the correction of the sag with respect to different tensions. We can see that given the weight and the length, the CS would be in the function of the applied tension. It's in a convex function and a decreasing function. It means that if we increase the value of the tension, the error from the sag will be smaller. From our previous analysis about the effect of the tension and sag, we can see that increasing the tension will actually make the reading from the tape smaller, while the effect of the sag is on the other direction. The sag will actually increase the reading from the tape. So we can see that by combining the effect of the sag and the tension, there is no way for us to find out the tension that can eliminate the sag errors. And this type of the tension is called the normal tension. And it could be represented as CS equal to CP at the normal tension Pn. So capital P equal to Pn as the normal tension. We know that CS is W square times L over 24 Pn square. And Cp is Pn minus P0 times L over A times E. Solving this equation, we can get the expression for the normal tension as 0.204 times W times square root of A times E over the square root of Pn minus P0. The equation of the normal tension is actually really hard to be solved. So usually we will given the normal tension for different types of tapes. For very heavy tape with the weight around 3 pounds, also with the length around 100 feet or 30 meters, the normal tension could be set as 51.8 pounds for 100 feet tape, or 26.5 kilogram for 30 meters tape. For medium weight tape with the weight around 1.5 pounds, the normal tension is set as 28 pounds for 100 feet tape and 12.8 kilogram for 30 meters tape. Here we usually assume that the cross-sectional error would be 0.005 inches square and the elastic modulus set as 3 times 10 to the power 7 pound per inch square. We have already learned 3 errors. Now let's see how we can remove the errors from our measurement mathematically. In this example, we assume that there is a 100 feet tape with a standard length of 100 feet at 68 Fahrenheit with a 20-pound standard tension and with the tape fully support. The observed distance between the 2 points with the tape held horizontal supported at 0 and 100 feet points only. And the 30-pound tension is 100.452 feet. The tape weight is 3 pounds, has a cross-sectional area of 0.01 inches square. Also, we know that the elastic modulus is 3 times 10 to the power 7. It wants us to calculate true distance between the 2 points. Now let's first try to summarize all the conditions we have from the experiment. First, we are given the standard length of the tape. L0 is 100 feet. The Standard temperature is 68 Fahrenheit. Standard tension is 20 pounds. And for the measurement, we have the applied tension as 30 pounds. The measured distance is 100.452 feet. And the weight as capital W is 3 pounds. We also know the cross-sectional area is 0.01 inch square, and the elastic modulus is 3 times 10 to the power of 7 pound per inch square. Another thing we want to know is the questions. So it wants to find out the true distance. So what's the true length from this measurement? Now let's see how we can solve it. First, we will consider the error from the sag. So we will try to get the correction from sag. So CS is W squared times L over 24P squared. So we have W is the weight of the tape, that is 3 pounds, times the length we measured, 100.452 over 24 times the applied tension. The applied tension is 30 pounds, which will give us the value as 0.042 feet. And then we need to consider the correction for tension. So we have the correction for tension as CP is P minus P0 times L over A times E. And we have capital P as 30, P0 is 20 times the length, 100.452 over A is 0.01 and capital E is 3 times 10 to the power of 7, which will give us the result as 0.003 feet. And then last week I tried to find out the true distance. So we first will use the measured distance, and we know that for the sag it will actually increase the reading from the tape, so we need to subtract the correction, so minus CS. And for tension it will actually reduce the reading from the tape, so we have to add the correction, and that gives us the result as 100.413 feet. And this is just the result we get about the true length. Now let's take a look at another example which will consider all the errors we mentioned previously. In this example, we have a 30-meter tape with a weight of 0.55 kg and the cross-sectional area is 0.02 cm square. It was standardized and found to be 30.005 meters at 20 degrees Celsius with a standard tension of 5 kg, and it was supported at 0 and 30 meters points. The tape was used to measure a distance about 89 meters over the terrain of a uniform 5% slope. The temperature was constant at 30 degrees. The tape was fully supported throughout, and a tension of 5 kg was applied to each tape length. The observed distance was 30 meters, and 29.5 meters. It wants us to calculate the horizontal distance between the points. So first, this one is actually measuring a sloping distance. So let's draw the measurement. The distance is approximately 89 meters. We want to find out more accurate values. The slope is 5%. And we also have some information about the tape. First, the standard length is 30 meters. And the weight of the tape is 0.55 kilogram, and cross-sectional area is 0.02 centimeters square. Also, we have the standard temperature as 20 degrees, standard tension P0 is 5 kilogram. Another thing we find during the example is like the 30 meter tape actually is found to measure 30.005 meter. So even though the tape marked as 30 meter, but the true length is 30.005 meters. So we set the true length of the measurement for 30 meters from the tape is 30.005 meters. We also want to get more information about the measurement. So the applied temperature is 30 degrees. The applied tension is 5 kilogram, which is also the standard tension. And we know that the length of the slope is very long, which is around 89 meters, and it's much larger than 30 meters. So we have to measure the slope for multiple times. In that sense, we actually measure them for 3 times. First one for 30 meters, second one is also for 30 meters, the last one is 29.5 meters. So the total length we measured is actually 30 plus 30 plus 29.5 meters. That is 89.5 meters. And we also specify this one L1, L2, and L3. And with all this information, we want to find the actual length, the actual horizontal length from A to B. Now let's see how we can solve the problem. First, let's check the tension. We know that the applied tension is 5 kilogram, which is the same to the standard tension. So the correction from tension is 0. We don't need to worry about it. Then let's go to check the impact from sag. We actually applied 3 tapes for the slope. And the first one is 30, second one is also 30, the last one is 29.50 meters. we need to check the sacks for each one of them. Let's see the sack 1. And we know that the calculation for the sack would be the weight square times the length over 24 times p square. And the weight of the tape is 0.55 square times the length is 30 meters over 24 times 5 square. Similarly, we can get the second one. The weight is also the full tape, and the length is also 30 meters, and we also have 24 times p square. It's the same to the first part. For the last one, it's a little bit different. It's actually not the full tape. We only have part of the tape. So it will be equal to the weight of the third part times the length of the third part over 24 times p square. So the weight for the third part is actually the weight of 29.5 meters. So it's 0.55 times 29.5 over 30, and the length we measured is 29.5 meters. And also for the bottom part is 24 times 50 square. In addition, we know that from our previous conditions, the 30 meters shown in the tape is actually 30.005 meters. So the true correction for sack is the summation of these three parts times the portion for the true value with respect to the male value. And that gives you the actual value for the sack correction as 0.045 meters. The next correction we will consider is for the temperature. And we know that the applied temperature is 30 degrees, the standard temperature is 20 degrees. Also for the tape, we are given the coefficient of temperature as 0.0000116, and then we can find out the correction for the temperature. So we will apply the correction for the temperature as T minus T0 times L and times alpha, which will give you the value as 0.0000116 times 30 minus 20 times the length that we estimated from the measurement, 89.5 meters, which will give you the value as 0.0104 meter. And we have to know that this is the correction for the temperature with respect to the 30 meter tape, but it's actually 30.005 meter, so we need to adjust the correction. CT prime will be CT times 30.005 times 30, that is 0.0104 times 30.005 over 30 is still approximately the same as 0.0104 meters. So we keep this value. The next error we want to consider is the error from the instrument. We mentioned a lot of times previously, like the true tape length actually measured 30.005 meter distance. So for the error from the tape, we will have the correction as 30.005 minus 30 over 30 times the length we measured, 89.5 meters. That will give you the value as 0.0149 meters. With that, we can try to summarize all the errors and get the true sloping distance. It will equal to the measured distance for the sag correction. It will actually make the reading from the tape larger, so we remove the sag correction 0.045 plus the correction for the temperature plus 0.0104 plus the correction for the instrument 0.0149, which will give us the result as 89.480. That will be the true sloping distance. And we also want to find out the horizontal distance. So with that, we need to first identify the vertical distance, which will be the sloping distance times the gradient, that is 89.480 times 5%. And with these two values, we can find out the true horizontal distance. That is s squared minus h squared. It will give you the value as 89.368 meters. So this would be our final answer about the horizontal distance in this problem. Besides the three major errors, there are also some minor errors. The first one is the random error, which is caused by the human limitations in observing measurements and manipulating equipment. Usually this error can be reduced by repeating the experiments. The second one is a mistake caused by the carelessness of the human surveyors, such as adding or dropping the full tape length, adding the foot on a decimeter, incorrectly taking a mark, or reading number incorrectly, or calling number incorrectly. In general, this type of mistakes can be removed by repeating the measurements by different group members. So that's all about the error analysis of the distance measurement. Thank you very much for your attention, and I will see you next week.